Hello folks, how's everybody doing? Hope you're doing fine. We have another fireside chat, as I like to call them. I think that better describes what we're doing here. First things first, we got the 7th Rational Physics Conference coming up, 3 weeks. If you plan to go, make your reservations, okay? And I hope to see you there, okay? And we're going to take assume where we left off, right? We were working with space. What is space? The modern notion of space is the same notion as the old notion of space, which is the ether. So space is ether, ether is space. As Nobel Prize Laughlin says, the modern vacuum, notion of vacuum, of space, etc., is the ether. There's no difference. It's just that nobody calls it the ether because it's taboo. And I think he pretty much hit it on the nose. Today's ether is the old ether. That's what space means to the mathematical physicists. They had to turn space into something. And most people visualize this ether as this space, this vacuum, the so-called nothingness, as somethingness. They visualize it as a bunch of particles. This is a good, I think, visualization of what they have in mind. Okay, not perfect, because there are different opinions out there, different versions, different proposals, but this gives you a ballpark figure. We have all these red particles on a white background, and encapsulating it all is some undefined, unspecified black stuff. Okay, now this is for an ether which is finite. And there's a finite ether and there's an infinite ether. There are different versions of that as well. But let's look at this one first. We have all these particles. All these particles are encapsulated, each one of them, by some kind of white medium that serves as a background to them, right, as a backdrop. And this is what it looks like up close. You have the particles of ether, and there's some white stuff that gives each of them a contour, okay? So the question is whether the ether is the same thing as the background, or the ether, in this case, the particles are something separate from the background. Are we talking about particles of ether in space, in which case we would have to define or identify what this thing space is? Or is the ether synonymous with the word space? Are they both the same thing? Are we talking about particles making up space? And here I have another little picture. That's what an ether without a background would look like. In other words, you wouldn't see the individual particles. What you would see is a single block. And again, we're talking about a finite ether in this case, right? We're not talking about the infinite ether yet. But we remove the particles because the particles are the same thing as space, so there is no backdrop, no contour to each individual particle. And the question is whether there's any motion. Looks like we're back to the Eleatics and Mr. Parmenides, who said there is no motion in the universe because there's no such thing as space, and therefore particles, such as Democritus proposed, had no space in which to move. So the particle cannot move into a new space because there is no such thing as space. And therefore, he said there's no motion. And this is what you have. You have no motion here. Why? There is no motion because there are no particles. Well, all we have is a single block. Okay? And so this is one vision of it. And these are questions that any proponent of ether would have to go through. They would have to answer each one of these questions, And one of them that you got to answer is whether the ether is infinite. And here you have the infinite ether. We give it no frame, nothing contouring it, because we're assuming it just extends forever. And again, this is an ether where the particles are different than the background. Okay. If you remove the particles and say that the ether is the same thing as the background, well, that's what you get. You get a blank nothing. So the question is, what are we staring at? What is that? Is that space? Is that ether? I mean, we can call it an X. We have to identify what we're dealing with, especially if we're going to introduce it into physics. Okay, and here's a different version of that. Okay, and you can see all the little particles just going everywhere. Is that what it is? All these particles just moving around in black space, whatever space is? Is this how we're going to do waves? Is this how we're going to do quantum mechanics? Are we going to postulate that there's a lot of vibrating fields which are particles which are really fields? Are we talking about energy? What is that thing that's vibrating in the background? You know, in fact, you know, the atoms would be in front, would be much bigger than this, right? And the question is this the background that we have out there? Is this space? Is this the real space? And if this is the real space, are these the particles that are brought in as virtual particles into the real world when they claim that some particle appeared out of nowhere? Are these the particles? And again, before we can say that there is such a thing as a virtual particle that appeared from nothingness, from the void, from space, we have to tackle this. This is the vision we have to analyze and find out, you know, what is that black stuff? What is the white stuff? You know, and again, if we remove the black stuff, what are you going to get? Well, you're just going to get this again. You know, you're going to get a blank screen. There, you know, so hopefully, if we're talking about virtual particles appearing from the void, you have to have this situation. And as you can see, there's two things here. There's something black and something white. The white is moving with respect to the white. The question is it moving with respect to the black? You know, that's one of the questions they would have to answer. And, you know, I cannot even imagine how complex this would be to do waves. For example, you know, if you are going to postulate that transverse waves are the vibration of the ether, well, there you have it. Okay, so is that what we're saying? How this can also travel straight is another question that the ether proponent would have to answer, right? And, you know, I like to look at it here the way I see it with God. This is how God would have to, you know, run his shop. He'd go nuts trying to govern so many millions of particles. I mean, you would think, you know, imagine God having to tell each particle what to do. This one's got to go that way, that one over there, and so on. You know, poor old God has got to go nuts. Or Mother Nature, or whoever you believe in. So we got a problem with the ether because, you know, the ether creates a lot of problems. And before you can even postulate the ether, you got to answer all these questions. What is the backdrop? Is the ether the same thing as space? Are there balls of ether? And, you know, and there's something else called space, in which case you got to define or tell us what that space is. What is space if it's different from the ether? If they're the same, does the, you know, if they're the same, there's only one entity, and then there's no motion. There's no individual particles that are moving because you're telling me that it's all the same. That there is no backdrop, there is no entity that encapsulates the particle and gives it shape. So these are the questions that a person who proposes ether must answer before they can do any of their theory. We're not even going to listen to their theory until they get past all these questions. And also the issue is it infinite? You know, what do you mean by infinite? I mean, are we saying that you just walk and walk and walk until you get tired? What is infinite? And that's why these words need to be defined before you can use them to analyze your foundations, your hypothesis, your proposal, your assumptions. Okay. Okay, so what have they done in mathematical physics? Well, what they've done is something like this. They have this thing called space-time, and some see it as a malleable background, which is what you see here. Others, like Mr. Blair, says it's rigid as steel, so some people, for their equations, need a malleable, flexible, fluid-like medium. Others need a rigid, strong, unbendable medium. Each one needs it for different equations. So if this guy's studying this aspect of mathematics, he's going to use the flexible one. If the guy is studying something else, well, he's going to use the rigid one. And it's like they never get they all talk about space-time. One's got a rigid space-time, the other guy's got a flexible space-time. One needs it to bend space. The other guy says, well, yeah, that's fine for gravity, but see, now I need to send a transverse wave, a gravity wave. And transverse waves cannot travel through flexible mediums. They cannot travel through liquids. They cannot travel through gases. And the more you want that transverse wave to travel more or less rectilinearly, the more rigid you have to make your space-time, or your medium, whatever is vibrating here. And so this guy needs a flexible space-time to produce the depression, which is going to be the gravity well that's going to produce gravity at the cosmic level. And the other guy needs to send waves. He says, well, yeah, I can't use your flexible depression-like ether space-time. I got to have a flexible one, because I've got to have a rigid one, to send my waves. And so, these things have to be settled before you come up with any explanation of how this universe works. We're talking about mechanisms here. We're not talking about math. We're not talking about verifying anything. This is before you design an experiment, you got to think. You got to sit back, grab a beer and do some armchair physics. That means you got to visualize what you're going to be doing. Then you can do the experiment. First, you got to design it. These people are skipping the design phase, and they're saying, oh, we're just going to go out there and measure. We're going to get some numbers, we're going to get some equations, and then we're going to prove it to our colleagues first, right, and then to the world. And the way you do it is you say, well, I measured, and this is what I got in conclusion. No, before you can do all that, please conceptualize it. And these people reject that as philosophy, as ontology, as metaphysics, or who knows whatever. Semantics. Okay, so that's one vision. Here's another vision. This is the field version. That's string theory is trying to merge quantum mechanics with relativity. And the way they do it is, they think that each particle out there is essentially a vibrating field. Here you have a field, or what they imagine as a field, and the vibrating of that is the particle, whatever a particle means to them. So a particle is not a little loose thing today, not under quantum field theory. It's this field that they're trying to merge with general relativity. They're trying to merge the little world with a big world, the micro world with a macro world, and they say, look, a vibrating field is what a particle is locally. Okay, and so what is that stuff? What are those? What is that cobweb? What are those lines? Where are they in the standard model? Well, of course, you won't find them there, because this is something that they pull out of their nose holes. Okay, they just don't have an explanation for these things. What do we propose instead? Well, here we're saying that we have a single thread. Here it is, and there's a single thread in all of space. That's all there is, and it twines around, converts into ropes which bind any two atoms which are made of the same thread, and light is simply a torsion of that thread, of those twined threads. Okay, and so the world would look like that anywhere. If you had God's eyes, that's what you would see out there in the universe. Okay, and so let's compare them side by side so we know what the differences are. Here's the ether particles on the one hand, and a single thread on the right hand side there. Okay, so these are the two, I guess you could say, competing theories, competing proposals before we start anything. So we're talking about really hypothesis, the assumptions. And we're saying, you know, either you have particles and you have a lot of questions with that, and of course there could be a lot of questions with a single thread, but that's the proposal. There's a single thread in all of space. It turns into atoms and ropes, and that's all there is floating out there. And space is nothing. What is nothing? We define it. What do we mean by the word nothing? What's the opposite of something? If something is that which has shape, nothing is its antithesis, and that's that which doesn't have shape. Now we have a definition we can use consistently, and so we have shapes in a universe that doesn't have shape. That's essentially the proposal. Okay, so in order to analyze the space-time, the ether, the space that they use in mathematical physics, we have to go back to the origin of ether, and we went all the way to the Greeks. Found out that they debated these same issues. So we haven't made much progress in at least 2,500 years. We're still debating the ether. Is space made out of something, space itself? Is there something in space that we can't see, such as particles? Or is there something in space, to use the word in, which is not exactly correct because you can't be in a concept. Nothing is a concept. But let's assume that, let's use that word. Is there a thread just, out there in space? That's all there is. Is that what we are? We're just this thread turned into atoms, turned into light, and we're all interconnected. All atoms in the universe interconnected. It's a totally different proposal. Do you believe in it? We don't care. The important thing is that you understand it. I always try to make that clear to people because people confuse believing with understanding. We're not here to convince you. We're not here to persuade you, even though we always do that anyway. It's human nature. But the point is, you have to separate science, objective science, from religion, from opinion. Okay? And so all we're interested here, or primarily interested here, is for you to understand what is being proposed and what the issues are. Okay? Okay, so we went back in time. We found out that the Greeks, they debated the ether, and we worked our way upwards all the way to the 17th century, and they started looking at the vacuum. If there is really a vacuum, if there's something separate from space, is there space and some other entity that fills space or that is space, like the ether, or is there some place out there or some conception even of nothingness, of there being nothing whatsoever in a region of space? Is there a true vacuum somewhere? Nothing. And so that debate started again in the 17th century, beginning, in fact, of the 17th century. And here's Mr. Birdie, and he ran an experiment in which he filled a long tube with water. He evacuated some of the water from the bottom after plugging the top of it. And he said, I produced space in that bulb over there. I produced empty space. I produced vacuum in there. So he had this tube, filled it with water, plugged it, evacuated some water from the bottom, okay? And there he's opening up the bottom, releasing some of the water. It drains, but it doesn't drain all the way. It drains only partially. And he says, up there where the bulb is, that's complete empty space. That's total vacuum. And some people didn't like that, but one guy who liked it was Torricelli, his countryman, and he did the same experiment. He did it with mercury, And what Torricelli added was that it was the weight of air which was pushing down and preventing the rest or the remainder of the test tube there of being evacuated completely. So it was the pressure on the reservoir of air, the air pressure on the reservoir which prevented the full evacuation of the tube. Okay. Well, some people, especially Mr. Descartes, who was a contemporary of these two gentlemen, he had a different idea. And he says, look, there is no such thing as empty space. In fact, any body, anything, any object is the same thing as empty space, because empty space is no different qualitatively than, especially quantitatively, but he also referred to qualitatively, that they're both the same. A body, an object, a thing is the same thing as empty space. And you say, how can that be? And he rationalized it like this. He said, a body is no different than the quantity in units by which it is described. In other words, he was talking about volume, all volume occupied by a body. He says, if you move the body, which has length, width, and height, well, space also has length, width, and height. And you don't leave the space behind, because that would be like leaving the soul of a body behind. When you remove the body, if you leave space behind, you're creating more volume in the universe. That was his reasoning. So he said body and space are identical. And so, when these folks did their experiment on the vacuum, he said, you're fooling yourselves. You haven't evacuated all the stuff from that little bulb. You left something in there, and that's the ether. You have particles of ether still in there. And, one of the rationale behind it was that, when you remove something, a body moves, something fills its place. How it does it, we don't know, but that was the theory. The theory was that you move a body, something fills its place. That came all the way from Aristotle. He had the same idea, and Descartes was essentially Aristotelian. Okay, what happens next? Well, around mid-century, 17th century, Mr. Guericke, Otto von Guericke, he does an experiment in which he evacuates a couple of hemispheres made out of copper, and he removes all the air from it with a little reverse air pump that he created there. He just pumps the air out of there. And he has, one case, several men pull on the outsides of the spheres to break it open. They can't. In another case, more dramatically, he's got 8 horses pulling on these two hemispheres, and they can't break them apart. Okay, so he shows how strong the vacuum that he's created in there is, and essentially he's saying, what you have is the pressure of air pushing it inward, just like Torricelli had said. Well, some people have problems with that, and so let me get this one here. They ran an experiment in England, people who copied essentially what Guericke had done, and that's Boyle and his right-hand man, Robert Hooke, who was his engineer, his lab boy. And Robert Hooke would do the experiments, and Boyle would report on them. And he reports that he produced the vacuum. And Mr. Thomas Hobbes, a contemporary of his, disagreed. He says he took the version that Aristotle took and Descartes did, that, all the matter was not evacuated from the glass chamber that Robert Boyle had created. So even though Boyle pumped the chamber just like Guericke did, he believed he had evacuated everything that was in there. He said there's no ether air in there, no wind, and so nothing he could detect. So he says, I created a vacuum. So there is a real empty space that you can create. And, for religious reasons, Thomas Hobbes did not agree. Thomas Hobbes was an atheist, and he thought that by creating empty space and calling it a thing, you were kind of creating this soul, this spirit, where you've got a thing that is not a thing running around. Okay, so he said, pretty soon all these pastors are going to try to interpret that for you, and they're going to say, hey, there's this nothing and it moves around. We can manipulate it. And he was worried about that. On the other hand, Boyle, who was a ultra-religious guy, he believed he evacuated the chamber. So sometimes you have these people that, you look up and say, oh, this guy's an atheist, I'm an atheist, so I'm going to follow him. And it turns out this guy might have the wrong idea. In this case, you got to make, your own decisions. You got to reason this thing out for your own self. You can't rely on anyone else. No one can think for you. Okay, so you got to figure out for yourself if through your own reasoning, if you really can create a vacuum. If there's really something called nothing out there, which is a contradiction, right? In other words, is there a true vacuum in the universe? What is space? And if not, is this space infinite? Is it made out of particles? Are those particles extending infinitely? You got to answer these questions. These are not issues that you do by proving. They're not unscientific questions, as the people in mathematical physics would like you to believe. No, these are questions that arise when you present a hypothesis, a set of assumptions. You have to finish these assumptions before you can continue to your theory. You got to answer these questions. If you're going to say that space is made out of particles, we want you to point to it and draw it and tell us what the shape of this thing is, because that's what an object is. If you're going to say that space is an object, that's what you got to do. And yeah, a lot of people don't like to get into that because they consider this ontology. They consider it outside the realm of physics. And no. First, we have the foundations of physics, and this is part of all these issues are part of the foundations of physics. So you must answer these questions. At least that's the position I'm going to take here. Okay. So this is what the issue was here. We have vacuum on the top and little water at the bottom, and the question is whether there are ether particles in that region or whether we have empty space. Okay. One guy who tackled it was Huygens, as we discussed the other day, and what he did was he said, look, he vouched for the wave version of light. And he said, look, what you have is light can go through that region. So even though you remove all the air out of there and there is no sound in there, if you evacuate this completely, you hear less and less sound. And I guess they couldn't hear it anymore after a while. And they say, oh, there's no more sound. And so you got rid of the sound, but light could still go through there. And he thought it was some medium that could propagate waves. He was thinking of waves. He was thinking really of spherical waves. He was thinking of it more like sound, where sound from a given point expands radially in all directions, spherically. And he thought of light in the same way. He said it's some kind of spherical wave that's coming out of the center of that bulb or somewhere in there. Okay, so he said you haven't gotten rid of whatever matter was in there. You just got rid of the big matter, but there's this ether in there that's vibrating, and that's light. That was his notion. Okay, so again, I wish I could travel back in time and show him a different version of this. And here's the version that I have as a proposal, and that's that you don't need matter in there. In other words, the white stuff in there, that's not filled with some kind of ether, some kind of particles or whatever. No, what you have is atoms, and they form the glass walls there. Okay, so the glass walls are all made out of atoms, the crystal structure of glass, silicon dioxide. And what the atoms do, they're all connected, all interconnected. All atoms in the universe are connected to all others. And so you have the torsion going from one atom to another, goes right through the chamber. So we can't see the medium, the rope, because it's such a thin thing, it's a carrier light essentially. So the torsion is there along the rope. and you see light going through there, but what it is, it's a torsion going from atom to atom, and from that same region, because there are particles in there. If you can see like a laser, because sideways, that means that the laser hit something that it stimulated, gave it a new frequency, and that frequency is being refracted towards your eyes. That's why you can see it sideways. If there were no medium, you would not be able to see light from the side. Okay, so that's the theory. In other words, what I'm proposing is that it's the glass that's made out of atoms. The atoms are interconnected right through the middle of the chamber, and that's why we can see light going right through the chamber, as Mr. Huygens, duly noticed. And we don't need a medium in there. We can I'm assuming we could achieve perfect vacuum, right? If we could remove every atom, again, anything hydrogen or above, right? We can remove every atom from that bulb, from the white region, we still would have light going through there, not because there's matter in there, but because light is mediated by an electromagnetic rope, okay, torsion along a rope. Okay, so that gives us a general feel for what's going on here. In order to complete what's happening, we're still in the 17th century, by the way. We can't get away from there because lots happened in the 17th century. It was, again, the age of the scientific revolution. That's what it's called. And to some degree, it was a scientific revolution. Not what I called science, but it is a revolution in the sense that people began to look at some of these things systematically. They started doing experiments, they started doing observations, they were testing different theories, okay, in their minds, and selecting them and say, well, I like this theory, I don't like that one. They had fights, they had arguments, they had debates, okay, usually through writing. And again, we're talking about a relatively small group of people in different countries, in France, specifically in Europe, right? France, Holland, England, Italy at the beginning of the century, and so on. And so they were debating and discussing these things. And something that happened parallel to light was magnetism and electricity. And you can consider the 17th century really the dawn of electricity. This is when electricity starts being noticed, specifically static electricity. That's where they start. And people begin to talk about electricity. And slowly they realize that electricity is not the same thing as magnetism. To that point, there was no clear distinction for people because electricity would do a little bit of attraction, so would magnets, and so they really couldn't tell the difference up to that point. But little by little, they began to realize that they were dealing with two different phenomena here, okay? And to start out, you really got to go back again in time. One of the things that a lot of people don't know is that, the Greeks already were aware of electricity. They didn't know what electricity was, but they were acquainted with a phenomenon, okay? And part of it was static electricity, but more importantly, they were able to find a fish, really a ray, and it was the electric ray. And the electric ray was in that region. They had an acquaintance with it. They had met the ray, and the ray gave them an electric shock, just like an electric eel would give you an electric shock. And so they said, oh, I got a shock. And so they didn't know what electricity was, but they knew that little animal, they had some special superpowers. And they did relate it to Zeus and his thunderbolts. Zeus controlled the electric bolt, and they kind of said, well, that's the power this little animal here has. He can give you a shock. He can give you, today we know, it gives up to 200 volts, right? So they can give you a shock, could kill some people, right? And here we have a couple instances where people write them. Several people knew about these things, by the way. Here's Plato, okay, and he writes in his Meno, one of his dialogues, right? You see, you seem to me, here's Meno talking to Socrates, right, in this dialogue. And he says, you seem to me both in your appearance and in your power over others to be very like the flat torpedo fish, that's what it was, the torpedo fish, who torpifies those who come near him and touch him, as you have now torpified me. And so he was referring to these shocking things that Socrates was throwing at him. And in the age of the Romans, first century AD, right, we have Scribonius Largus, who was a physician. And he suggested that it would be nice to get a shock from one of these fishes, especially if you have, some disease such as, gout. And he says, for any type of gout, a live black torpedo, and the torpedo was what they would call this electric ray, okay, should, when the pain begins, be placed under feet. So now you know how to cure your gout, okay? The patient must stand on a moist shore washed by the sea, and he should stay like this until his whole foot and leg up to the knee is numb. Now you got to take this electric shock, right, by standing on a fish, right? This takes away the pain and prevents pain from coming on if has not already arisen. In this way, Antares was cured. Maybe Antares died completely, for all we know, maybe you call that a cure. Okay, so they were aware of electricity or shocking or something, but nobody researched it. No one looked at it any deeper than that. It was just maybe some static electricity, some amber that they rubbed, right? And some fish that they touched. That was it, and it never went beyond that. And you got to go really farther into time. They don't deal really with electricity either. They deal really with magnetism, but it's going to give us an introduction into electricity. And we're going to go to the 12th and 13th century, and here we find one of our dear abbots from England, and he is the first one to write about magnets, specifically about the compass, okay? And the Chinese already were aware of the compass, not really of the compass, but they had some device similar to a compass already in the Han Dynasty, which was 200 years before Christ to 200 years after Christ. Those 400 years, the sailors over there in China were already using some kind of lodestone that floated in water, and they could tell south from north. And Neckham is the first one to write about it in the West, even though he's just telling us what the sailors already were using, okay? So he's just describing something that was already being used. But he says the sailors, moreover, as they sail over the seas, when in cloudy weather they can no longer profit by the light of the sun, or when the world is wrapped up in darkness of the shades of night, and they are ignorant to what point their ship's course is directed. These mariners touch the lodestone with a needle, which the needle is whirled around in a circle until when its motion ceases, its point looks direct to the north. Okay, so that's our first extant description of a compass. Okay, and obviously he's writing in the 12th century, but I'm sure this existed a lot earlier than this. Nobody else wrote about it, as far as I'm concerned. They did write about it only in China, but nowhere else on the planet, as far as I'm concerned. It's going to be this gentleman here, Petrus Peregrinus de Maricourt, and he's a French mathematician. He writes a letter to his friend, and he talks a little bit about a magnet. He's so excited in his letter, you should read it. It's like 10 or 12 chapters long, and he's excited because he's found out some properties of the magnet, and this is one of the properties he finds out about it here, which is very interesting to read. It says, if you wish the stone, it talks about the lodestone essentially and how it attracts iron. He says, if you wish the stone according to its natural desire to attract iron, proceed as follows. Mark the north end of the iron, and towards this end approach the south pole of the stone, when it will be found to follow the ladder, or On the contrary, to the south part of the iron present the north pole of the stone, and the latter will attract it without any difficulty. Should you, however, do the opposite, namely, if you bring the north end of the stone towards the north pole of the iron, you will notice the iron turn around until its south pole unites with the north end of the lodestone. The same thing will occur when the south end of the lodestone is brought near the south pole of the iron. Now, how's that for a description of a magnet? Okay, and you might laugh. You might laugh and say, Jesus, these guys discovered what we take for granted these days, right? We know what a magnet does. You got the north to the south. Typically, when you buy them, they're colored, so you know which one's the north, or they're got a little N, a little S, and so you say, oh, I know what it does. This one's facing that way, that one's facing the other way. But and so you kind of laugh at Peregrinus here because, which by the way means pilgrim. And Peregrinus, he's discovered this. He's so excited to be able to tell his friend about it. It turns out that to this day, we still use Peregrinus' description. There is no explanation, no mechanism of how a magnet attracts another. So you might laugh at Peregrinus. You're only laughing at your own ignorance, because that's all we have today. We have north attracts south, positive attracts negative. That's all we have. And, they asked Richard Feynman, BBC asked him, and you also can look up Sean Carroll. He gives a presentation where he laughs at the insane clown posse, which says, freaking magnets, how do they work? And he said, of course we know how they work. Well, why don't you tell us, Sean? Tell us how they work. Tell us the mechanism. Otherwise, the insane clown posse is vindicated. You don't know how they work, okay? And so, yeah, we still are using Peregrinus' explanation, which is not an explanation. All he did was describe, north attracts south. Did he know exactly what the mechanism is? No, he was excited just to be able to describe this phenomenon he just noticed, all right? And he didn't put any mathematics behind it. He just said, look, north attracts south. That's it. And we still have his explanation, whatever, if you call that an explanation, right? Okay, where do we go from here? Well, some people wrote about the magnet. And one of these guys, the most famous probably, is William Gilbert. And he writes in the 1600, he writes on the magnet. He writes a book, pretty lengthy book, like 400 pages. And he writes on the magnet. And again, he essentially makes no improvement over Peregrinus. But the main point here is that he still, up to that time, 1600, okay, 1600, he dies 1603, 3 years later. Up to that time, they still hadn't figured out the difference between electricity and magnetism. They were not clear. They were starting to notice maybe some differences, but no one wrote about it in a clear-cut way. And this is pointed out by Mr. Guericke, who also did a lot of studies on not only, which I showed the other day, he did experiments on vacuum, but he also looked at electricity, specifically static electricity. He does his experiment up in the 1650s all the way to 1663. And, oh, by the way, that date is wrong. It should be 1602, okay? Hopefully he lived a little more than 20 years. So that's 1602, that's an error. But in 1663, he finishes his studies, essentially, but he writes about it in about 9 years later, in 1672. He publishes this book where he talks not only about the vacuum, right, as you can see there, vacuospatial, but he also talks about, electricity, static electricity. And he writes the following, specifically referring to Gilbert, who referenced Peregrinus. And he just says the following: writers who have written on magnetism always confuse it with electrical attraction, although there is a great difference. Gilbert, in his book De Magnete, claims that electrical attraction is caused by the effluence of a humor, that the humid seeks the humid, and this is the cause of the attraction. And he says, humidity does not play any role, but the attraction is brought about purely by the agency of an effluent, by which the air is disturbed. So Guericke doesn't understand what causes this. He doesn't really know what electricity is, but he says there's a difference between electricity and magnetism. He says, after the initial impulse, the air returns to the amber. Again, amber was the name that was the substance that the Greeks used, and it was known as electron or electricity, and that's where the word electricity comes from. The Greek word for amber. Okay, again, taking with it little particles. Again, he's thinking of particles. He's thinking of the ether, but he's the first one to really write about and notice that there is a significant difference between electricity and magnetism. And we're going to find out about that in 2 seconds, why he came up with that conclusion. He says, he writes in it about his experiment, and he says, when that sphere is stroked or rubbed, not only does it attract all light objects, but it sometimes arbitrarily also repels them before attracting them again. Okay, he's run an experiment, which we're going to see in a minute here. It's a sulfur sphere globe that he turns around and creates static electricity through friction. Okay, he says, we take the attraction of the sulfur ball as electrical in nature and operating through a conservative potency. Cannot admit that the air plays a role in producing the attraction. Okay, so he's eliminated humidity and he's eliminated air. Okay, he says there's something else going on when we have electricity. Experiment visibly shows that this sulfur globe, once it has been rubbed, also exercises its potency through a linen cord up to a range of a cubit and more, and can attract at that distance. Okay, and some people had problems with that because he was saying, look, this electricity stuff, whatever it is, somehow goes through linen. You can put a barrier there and electricity can still go through it, the static electricity. Some people had trouble with that, and they said, no way. You're saying electricity goes through things? And again, people were probably imagining particles going right through the linen, maybe, but this is what Guericke writes about, and people were a little scared about this thing, saying, how can this possibly be? What is this thing called electricity? But the point here is that he's able to rub something, this ball, right? In fact, let me show it to you. This is what he's got in mind. Here, I'll show it to you. Okay? And it shows how it attracts things, okay? And let's go with where it starts in a minute here. Okay, here it goes. Okay, this is the ball, the surfboard ball. He has it rotated and has a little bit of friction there. You can do the friction with your hand. Okay, just turn it around, rub it, and here's a modern version of it. Okay, and now you can see it picks up light things and it holds it onto the surface. Okay, so this is what Guericke noticed. He said, look, this is not magnetism. This is electricity. This is something else. And so we have electricity and we have magnetism. This one is different than the other one because you're not using metals like lodestone. Lodestone, they take 2 pieces of lodestone, say, yeah, it attracts iron. They could do that. But then here they're saying, look, I rub a ball and I produce this other effect here. And so this has to be different than this other thing. At least that was his conclusion, Guericke's conclusion. Looks like this stuff is a little different than this other one. And now we're starting to see, like I titled this thing, the dawn of electricity. Suddenly people start saying, oh, this is a different phenomenon, okay? And again, one of the, let's see if, this is a more sophisticated version that Guericke also built. Okay, and here you'll see the more sophisticated version. It's a machine that he can, pedal, or with his hand, he can hand pedal or foot pedal it, right? Here you can see how it turns that ball, it rubs it, and now you can see the static electricity in there, how it bends that little thing there, you know. And so he does these experiments, and he realizes that he can produce these phenomena. Okay, I guess he invented the bingo thing there. You know, he does these experiments. He's able to show that, you know, electricity is a little different than magnetism, and his ideas get spread around, and they eventually reach England. You know, because England was copying a lot of the stuff that Guericke had published. They had heard about his work with vacuum. So so Boyle goes out there and he does his little glass jar thing where he evacuates that jar and says, yeah, there is vacuum in there. And then he also takes, not so much Boyle, I'll clarify that in a second. He also takes this this static electricity that Guericke had produced, and they're going to bring it over to England and say, oh, this is a great idea. And we're going to find out that, you know, the Royal Society, which had formed by then during the reign of Charles II, they have all these, you can say this is the cutting edge of technology in those days, of science. And group of these people, they analyze all these things. They, especially, you know, what Guericke had done, and they said, look, this guy also says that he produced static electricity. And he does it by rubbing this sulfur ball. Okay, and they're going to take that and they're going to improve upon that. Specifically, what they're going to do is they're going to take that glass enclosure in which they created vacuum, they evacuated all the matter from it, or so they thought, and they're going to start to rotate it. And when they rotate it, they also do the Guericke trick. They put their hands on it. What are they going to find? Well, they're going to find something so weird. They're going to find plasma. The plasma ball, the first notion of the plasma ball. I'm going to continue with that next time, but let me just show you essentially what one of the fellows of the Royal Society, his name is Hawksby, and Hawksby is going to discover this. He turns the glass enclosure, it's evacuated, okay, so it's we have vacuum in there, okay, and he's gonna place his hands upon it, and he's gonna see this. He's gonna see this blue light, and he says, "Oh my God, look! You know, I produce this light in the darkness, all right, and it's gonna be this thing that is really gonna turn things on for electricity." This occurs at the beginning of the 18th century, but it's still, you can say it's got its origin right at the end of the 17th century. Okay, with that I'm going to continue next time around, but to summarize, you know, we need to get a hold of what is the ether, what is space, and we're going to introduce here in the 17th century, we already had the magnet, we had an idea about the magnet, but now we're going to introduce electricity. And electricity is also going to be thought of as being this ether out there. You know, we have ether for everything. We have ether for light, we have it for magnetism, and now we have it for electricity. And right at the end of the century, 17th century, we get these weird experiments in which static electricity is created artificially. For the first time, we are able to create some kind of electricity. And the British, especially the Royal Society, is going to take this idea, develop it further together with a vacuum. They're going to have the vacuum rotate here, and they're going to put their hands on it and create this glow, this purple glow, blue glow, and that's going to take off in the 18th century. And we're going to see all the nice things that are going to happen in the 18th century, which is quite funny, really. But we'll see you next time Sunday, and I'm going to continue with this line of thought. So keep all this in mind for next time. We'll see you then. Bye-bye.